Hello, I'm back there.
Okay, Ajit, yeah. The people have let in, and you can start whenever you want.
Okay, lovely. All right then. Good morning. I'm sorry about this. I thought the lecture was at 10:30, and I was going to another venue, but I now I realize it's at 10 o'clock. Okay, I'm going to be talking to you about white dwarfs. Now, some of you may remember, and those of you some may not have been there at the time, but towards the beginning of the course, I gave some lectures on black holes. There are 3 lectures called Black Holes Across the Mass Spectrum. The black holes are compact objects. You cannot have objects more compact than black holes because they have a size of 0 and they have infinite density. There's a singularity. So today I'm going to talk to you about white dwarfs, which are again very compact objects. A typical white dwarf has got a mass, let's say about 1 solar mass, a little bit less, 0.6 solar masses. But the size is 100 times less than the size of the sun, the radius. Which should mean that the density of the white dwarf, which goes as 1 upon r cube, the density of matter, would be about 1 ton per centimeter cube. So this is an altogether different kind of matter from what we are generally used to. And so these objects are very enigmatic. But as it happens, the physics of these objects is both very elegant and rather simple, in the sense that one can apply well-known laws to the study of these objects and come to very fine conclusions about them. Then the name of the phrase white dwarfs is always associated with the name of Professor Subramaniam Chandrasekhar, who proved very famously that white dwarfs have a mass limit. So you are almost getting to the end of your course. So I'm sure that you must have heard of many of these concepts before about white dwarfs and neutron stars and so on. But what I intend to do today is to take you a little bit deeper into the realm of white dwarfs. So the same thing that you have done before, as a part of a larger, a larger concept, I would now focus on more deeply. So, what I'm going to do today, I've put out the topics here. I'll revisit the Hertzsprung-Russell diagram. I'm sure that you have heard about it quite a lot, and stellar evolution, just in a couple of minutes. And then I'll talk about how white dwarfs were first discovered, and then the white dwarf theory, then the Chandrasekhar limit, then white dwarf cooling, and then white dwarfs as progenitors of supernovae, supernovae type 1a. So white dwarfs are truly very interesting objects because they're right at the forefront of cosmology at the present time. So it's not clear to me how much I'm going to be able to cover in the 2 lectures, but rather than try to fit all this in, what I'll try to do is to go a bit slow and then explain the complex concepts. What I would like to do is to stop in between and ask you to ask questions because those will be very vital at this point. And such a lecture should really be given face on, but unfortunately it cannot be. So Santosh or whoever is the organizer now today, please remind me about 10:35 or so about the questions if I forget to stop. All right, then starts. So clearly, the most important star we have is the sun, and is the closest star. You have heard about it quite a lot. And this is these are pictures of the sun. I mean, I didn't want to pick up the slide. So you have got the sun here in the usual light, and then you have got here the sun in special. I've forgotten what wavelength this is, but you can see this great flare coming out of the sun, and you see that the size of the flare is comparable to the size of the sun. And then you have got the sun here at the time of the solar eclipse. And here you've got the different parts of the sun. So right at the center, you've got the core, which is true with all stars which are actually producing energy. And the temperature of the core for the sun is about 15 million Kelvin. And there the nuclear reactions take place. Then the energy which is generated, and the total amount of energy we know is 4 into 10 to the 33 Earth per second. That amount of energy has to be transported out. Because if it was not, then the sun would soon explode because it would get hotter and hotter, and which would lead to uncontrolled nuclear reactions. So the energy can be transmitted, is taken out transferred out through either radiative processes, and this is the radiative zone in which these processes occur, or they could be through convection, and which is right there on the top, where the temperatures become lower and the conditions for convection are met very well because the opacity increases. Right, so now you know that the sun has a mass of 2 into 10 to the 33 grams, and it has got a radius of 7 into 10 to the 10 centimeters. Right, that is 700,000 kilometers. Now, we need to remember these numbers because I'm going to use them extensively. Everything about white dwarfs will be in terms of his measurements of the sun. So our sun is the standard, 1 solar mass and unit radius. Okay, so then in comparison, you have got these stars, which are, so you see that here you have got the dwarf stars with a mass which can go up to 0.08 solar masses. You can't have stars with less mass than that because then there will be no reactions taking place in them in the center. Then you pass through a normal star like the sun. Then you have got the white, blue-white supergiants, 100 to 150 solar masses. And then you have got the immensely large red giants, okay, which is not the main sequence phase of a star, but it is the phase in which the star has finished going through one stage of evolution where one particular fuel is exhausted at the center, so the center collapses and the rest of the star expands. Right, so now we don't want this one. Now I come to the Hertzsprung-Russell diagram, which is very important for us to understand the special nature of the white dwarfs. So you see that in the Hertzsprung-Russell diagram, which I'm sure that you have studied before, and I would strongly advise you to understand the diagram very well because it is so important for the understanding of the stellar structure. Right, so on the y-axis of the diagram, you have got absolute magnitude, which decreases upwards, which absolute magnitude is the logarithmic representation of the luminosity, the total amount of energy which is emitted. On the x-axis, you have got the temperature. And so the luminosity increases upwards, but the temperature decreases as you move away from the origin there. And you find that a vast majority of the stars are along this particular sequence, this particular locus, which is one of the main sequence. And when this diagram was first plotted by Hertzsprung and by Russell towards the beginning of the 20th century, so at that time it was immediately noticed that you see the stars here of low temperature and low luminosity. So all low temperature, low luminosity stars are at the right of the diagram, and the high temperature, high luminosity stars are on the left of the diagram. And here you have got another set of stars which were not understood at that time. And what are these stars doing here? And what is the relation to stars here on what was called the main sequence? And one sure way of understanding these things is to look at the Stefan-Boltzmann law. So you know that we can consider a star like the sun to be a black body, meaning that a black bodies are not black, they're emitting radiation. And it's an approximation. So for the sun, for example, the emission of the sun fairly closely resembles the emission of a black body with a temperature of about 5,800 Kelvin. So in general, you know that the total amount of energy that is L emitted by a black body is 4 pi r squared sigma T to the 4. That is the effective temperature because it's a representative temperature. So what does this tell you? Now let us look at objects here. So these are high temperature objects and these have got high luminosity. And therefore they also have, and here you can say from here that they will have certain radius. So if you know the temperature, you know the luminosity, you can find the radius. Now what about objects here? Again, it is the same story. But let us compare objects here where it is low temperature and low luminosity with these objects which have got high luminosity, because you see that from the x-axis, from the y-axis, you'll find that they've got high luminosity, 100. The temperature here is the same as the temperature here. So which means that from the Stepan-Boltzmann law, we must know that this has got a large radius, and which is why they are called giants and supergiants and so forth. And so therefore, if I have objects called white dwarfs and which are located somewhere here, their luminosity is so much lower than the luminosity of these objects. The temperature is the same, which would mean that the radius of the stars is very much lower than the radius of the stars on the main sequence. This was a reminder to me that the lecture was at 10:30, which was wrong information. All right, so here is a modern version of the Husband-Russell diagram with lots and lots of stars on it. See how beautiful it is. And here you have plotted the color, and here you have plotted. This is from the satellite. I forgot to name the satellite. I'll tell you that in a moment. And then each one of these dots represents many stars, as you can see from this color bar. Okay, that's the position of the sun. All right, now a star like the sun, which is on the main sequence, always burns hydrogen in the core because the temperature is about 15 million Kelvin. Okay, and then it is converting hydrogen to helium. This is technically not burning, but it is nuclear fusion which is taking place. Then the energy is being transmitted out, and what you see is the photosphere, which is at a much lower temperature. So now, when you exhaust the hydrogen, what happens is that the central part, the temperature reduces because energy is no longer being produced, and therefore the pressure reduces, and the gravity becomes therefore dominant, and the part collapses. And when it collapses, then the next stage in the nuclear fusion story would be that the helium which is present here is raised to higher and higher temperature because of the gravitational energy which is released in the collapse. And then that energy, so if the temperature reaches about 50 million Kelvin, okay, then helium starts fusing to the higher elements like carbon, oxygen, and nitrogen. So now, but what is the condition? The condition is that the mass must be sufficiently large. So for stars like the sun, the mass is sufficiently large, and therefore the collapsing mass is sufficiently large, and therefore the temperature is sufficiently high. If it is not, then you will get what is known as a helium white dwarf. But I'll tell you what's a white dwarf as I go along the lecture. So now here, when you exhaust helium, you again go through a phase of contraction of the center and an expansion of the outer layers, and that goes on and on and on until if the mass of the star is more than sufficient, and let us say it is like 20 solar masses or so, then more than 10 solar masses, then you will finally arrive at a situation where at the center you have got iron, and then you have got progressively lighter elements as you go forward until you have got a thin shell of hydrogen. And for when this happens, you no longer can have a collapse in the center. That is because you can have a collapse, you no longer can have nuclear generation. That is because binding energy for iron is the highest. And you have learned all these things. But I need these things in my arguments about white dwarfs. And so let us see what happens here. Is that first you start with the stellar cloud. This is depicted in Husband-Russell diagram. And the cloud contracts for whatever reason. And then as it contracts, the temperature at the center keeps increasing until it reaches the main sequence and the hydrogen fuel starts. And then you go through the cycles that I mentioned. One element after the other is being ignited until you end up with a supernova. But we are interested in the situation where the mass of the star is less than several times the mass of the sun, in which case typically you would get a white dwarf in the center. You wouldn't go to a supernova stage at all. Right? So this, as you know, is a planetary nebula, which is called the Ring Nebula. It is that when the center contracts, the outer parts explode, but finally when a white dwarf is formed, then the surface layers of the star are thrown out in a gigantic explosion. If, on the other hand, the mass is sufficiently large, then instead of forming a white dwarf, you form a neutron star or a black hole, and then the explosion is much larger, and it is known as a supernova. Now, at the end of tomorrow, I'll be telling you about how white dwarfs also can collapse, can have rapid burning to produce a supernova. Right? So here is a diagram which I believe I showed to you some time ago, but may not remember it. As to what happens in this diagram, is that here you have got the initial mass of a configuration. And if that mass is less than 1% of the mass of the sun, then the equilibrium configuration that you get is governed by atomic interactions between the atoms. You get a gas planet or a liquid or solid planet. If the mass is between 1% and 8% of the mass of the sun, typically, then you get what is known as the brown dwarf. In a brown dwarf, there is just very marginal amount of nuclear fission taking place, and the object can be detected only because of the stored energy which is being emitted, and you have to detect it in the infrared. Then, when the mass is less than about 0.25 times the mass of the sun, 25% of the mass of the sun, and then the object, what you get at the center, is a helium white dwarf. It's predominantly made of helium. So the next mass range up to 8 solar masses. You'll get a carbon-oxygen white dwarf and a planetary nebula outside, and then you get oxygen, neon, magnesium white dwarf, and at a higher mass range you get a neutron star, and at the highest mass range you get a black hole. These numbers, of course, are approximate, and they keep changing as the theory improves. Right? So now, after this story, I use the word white dwarf quite liberally, but let us come to white dwarfs. But first, how were they found? But so what is a white dwarf? A white dwarf is a compact object. It has got a very high temperature, 10,000 Kelvin and so on. Okay, and so we could call it a star because for all practical purposes, it looks like a star. So 3 such objects were discovered in the early 20th century. Meaning, so there is a 40 Eridani B. It was discovered by Russell. What Russell is the same Russell from the HR diagram. And what he noticed is that this particular object was at a crazy point of the diagram. And then he said that it is a very unusual object. Then Van Manen discovered another similar object, which was in a wrong part of the Husband-Russell diagram. But the most interesting one, and which is what you hear about, and people believe this is the first white dwarf, but it's actually the third one, is Sirius B. You know that Sirius is the brightest star in the sky, of course, after the sun, brightest star in the night sky. And then Sirius, close to Sirius is a star called Procyon. But Sirius itself has got a very close double, and that double happens to be a white dwarf. Now, all these 3 objects were discovered. They're all within 5 parsecs, within 15 light years of the sun. So it was pointed out by Eddington. He said that, look, if within 5 parsecs you've got 3 such objects, and the galaxy is much, much larger than that. So he said that these objects must be very common. They're strange, no doubt, but they are not uncommon at all. They are very, very common. Right, so here are a picture, modern pictures of Sirius A. This is with the Hubble Space Telescope, and here you can see this is Sirius B, the white dwarf, and then here you'll see the same white dwarf here with a lot of image processing which has been done. You can see here, and 40 Eridani B. The interesting thing is that this is a double star. Eridani B is a triple star actually. You've got A, B, and C, and it is B which is the white dwarf. Whereas Van Manen 2, that is an isolated white dwarf. Now, it's much easier to find white dwarfs when they are in systems like this, because you see the peculiar motion of the main star and therefore the companion, and therefore you can derive the existence of the companion from the motion of the star. And so you'll see a beautiful example of that here. So before that, this one is a modern picture of a globular cluster, M4. And you see that this is the central part which has been observed by the Hubble Space Telescope. And each one of these dots, not the circles, but the dots in them, each one of them is a white dwarf. So we had to wait until 1910 to discover 3 white dwarfs. But now if you just point the Hubble telescope at a globular cluster, you can get dozens of them. You just see there's a very small region of the globular cluster. And so here, here you'll see the positions of the white dwarfs. So you see that the main sequence, the positions are here, much below the main sequence and to the left of the diagram, which means that the temperature is high because temperature increases from the right to the left. And the fact that they're so much below means that they're very dwarf objects, and which is why, which is what drove people crazy. They're very puzzled. They said that what are these very dwarf objects, right? So now you see here is a very beautiful diagram. Now this is the motion of, this is Sirius A, and this is Sirius B. So so Sirius B, and you see that they are going around each other. So the point is that the person who first discovered the existence of Sirius B was somebody whose name all of you will be very familiar with, and that is Bessel. I'm sure that all of you have struggled with Bessel functions in your mathematical physics courses. Now, the same Bessel, which is quite common, and the greatest mathematician of all time, Gauss, he was also an astronomer. So here you have got here you have got Bessel, who also did astronomy, and he looked at the position of Sirius. Of course, he didn't know about Sirius B. Now, this is a modern version of it. These are not his observations. You see, from 1900 to 2000, you see that how, Sirius A, if it were moving by itself, it had no force acting on it, then it should be moving in a straight line. But here you see that its motion seems to be wiggling in the sky. So when Bessel noticed it, he inferred that there must be a companion. I don't know. I don't know how far he went. Whether he measured the mass, also estimated the mass. I'll find that out later. Okay, so this companion was actually this was observations 1834 to 1844. The observations take a long time because this is 100 years, and here Bessel did it in just 10 years. Okay, so then you see that Albert Clark. So in 1867, he was able to observe the companion. And once you know that the companion is there, you don't require a very large telescope to observe it. You just have to do that very carefully. So here is again, this is not an interesting picture, a picture of Sirius B, which is the old one. And so let us see what are the properties of this particular object, and we'll show you why it is so strange. But these numbers are not modern numbers. There's a lot of improvement on them as you go along. But these are the more or less original numbers. So this is the mass of the object. Because it's a binary, the mass can be estimated. And the mass of the object was estimated to be between 0.75 and 0.95 solar masses. Right? So this was a pretty high mass object, almost close to the mass of the sun. And then the luminosity, of course, was much lower. And which is why this object was in the lower part of the Hertzsprung-Russell diagram, the lower left-hand part. Temperature is around 8,000 Kelvin. And so what is the radius? Just apply the Stephen-Boltzmann law. And the radius was found to be about 1.9 into 10 to the 4 kilometers. You know that the radius of the sun is 7 into 10 to the 5 kilometers. So the radius was very much smaller than the sun. So then what would be the density? The density was estimated to be about 4 into 10 to the 4 grams per centimeter cube. So this is completely crazy. Meaning that if you, this kind of a density is very high density even compared to the density of solids of the Earth, which are typically about a few grams per centimeter cube. So if you take a gas and then you compress it, you expect that it will change phase at some point. You cannot even imagine on Earth a gas with such high density. And so then the question is, how was it there in the stars? You must understand that when this density was first discovered, was measured, estimated, Now, the actual the nature of the stars was not completely clear, and people did not know that it is nuclear fusion which is generating the energy, right? Because the nuclear physics was just then being understood. Okay, similarly, there were quantum mechanics which are known, and they, in fact, did not even they were not 100% sure that the stars are gas or liquid or what. So you see that, but even if you say that it's a liquid, you know that the density of water is 1 gram per centimeter cube. So what kind of a liquid would be this so dense? Of course, the ideas were changing very rapidly, and people like Arthur Eddington, astronomers like Arthur Eddington, were very, very insightful. And Eddington wrote a book in 1926 called it's on the theory of stars, the internal constitution of the stars, in which the entire modern concept of a star was described. Right. So now let us see what happens. Is that the radius was determined also using a gravitational redshift by Adam in 1926, and which was considered to be another great demonstration of the correctness of Einstein's theory of relativity. Now, in the same year, in 1926, Fermi and Dirac discovered the Dirac Statistics. So there's a paper by Dirac on the theory of quantum mechanics in which this is there. Okay, and then Fowler, who was an American astronomer, so he immediately said that white dwarfs could be supported by degeneracy pressure. So I'm sure you know what is degeneracy pressure, but I'll describe it at length very soon. And then a few years after that, Chandrasekhar gave his mass limit on white dwarfs. There's also interesting work between this is 1929, Chandrasekhar 1930, but before that, before Chandrasekhar's work, there are other people like Stoner who also got important new insights into the structure of white dwarfs. Okay, so if you look at the modern numbers here, so you've got a radius of Sirius B. It is the correct radius, and then you've got the luminosity also better measured, and the temperature is 25,000 Kelvin rather than the 8,000 Kelvin which is estimated here, and therefore the density turns out to be not 10 to the 4 grams per centimeter cube, but it is 3 million grams per centimeter cube. Okay, so this is 3 tons per centimeter cube. So everything which puzzled people here would have puzzled them even more if they had got the correct numbers. So, so what is the size of the white dwarfs? So you have got the size of the Earth here. The white dwarf is so much lesser, smaller than the Sun, but it is comparable to the size of the Earth. And here you have got a small little neutron star, which is of 10 kilometers. And just like a white dwarf at the size of the Earth, the neutron star is a size which is comparable to the high mountains on the Earth, Mount Everest, for example. And then, of course, you have got the black hole with zero size. As I have explained to you, the neutron star has got a size of 10 kilometers. So when you look at the density, and if it is a few tons per centimeter cube, the density of the white dwarf, and that is comparable to if you take a African elephant, which are typically larger than Indian elephants, and then you crush it into 1 spoonful of matter, then you get the same density as a white dwarf. And here the neutron star densities, which are nuclear densities, 10 to the 14 grams per centimeter cube. So if you take all the people on the Earth existing now and put them in a pan and 1 spoonful of neutron star matter in the other pan, you get the same mass. And black holes, of course, the row goes to infinity. Now, when as they discovered more and more white dwarfs, then another very strange thing emerged. So you see that the stars here, the black dots, these are main sequence stars, proper stars of the main sequence. And then you will find that their radius, because this is log scale, radius and mass. So you will find that the radius of the white dwarfs increases with mass. Very roughly, you can take R proportional to N for stars like the Sun. But here you see that the radius of the white dwarfs actually is much smaller. Okay, no, not only smaller, but the radius decreases as the mass increases. Right? So this is very strange because as you add mass here, the radius increases as the mass increases. In this case, the radius decreases as the mass increases. And in fact, it is that fact which leads to the Chandrasekhar limit, as I'll explain to you. And so here is the Chandrasekhar limit. White dwarfs are maximum mass, and this is the approximate value. But you should put an equal to sign here, approximately equal to. And the most beautiful thing about this relationship is you see that on the left, you have got an object which is astronomical in size. This mass limit, is 1.4 solar masses. On the right, you just have the fundamental constants, H, C, and G, and the mass of the proton. So how incredibly beautiful this is, because just see, you know that we can work in units in which C is equal to 1, H is equal to, H cross is equal to 1, and G is equal to 1. And in those units, the Chandrasekhar limit is simply equal to the reciprocal of the square of the mass of the proton. So clearly there is something extremely fundamental about it. I mean, whatever theory changes, this is not going to change. All right. So I'll stop here now. And are there any questions? One moment, I can't see you people. So Santosh, how do I see if there are any questions? Okay, Abhijit Das has raised his hand. Okay, please ask. Abhijit, please ask your question. Santosh? Is anybody hearing me at all? Can you people hear me? Can you hear me at all? संतोष तू लेक्चर मध्ये होतास का? नाही, कारण काय आहे की मी बोलत होतो तर लोकांना ऐकू येतं का? आता मी क्वेश्चन विचारलं, दोघांचे हात वर गेलेत पण त्यांना कोणीच हे सोडत नाही क्वेश्चन विचारायला. ओके ओके, एक मिनिट. मी कर, मला प्रिव्हिलेज आहे का? ओके, अनम्यूट. Please unmute yourself.
Yes, sir. Yes, sir. Yes, sir. So now I could.
So tell me, what is the question?
Actually, sir, maybe I would have asked this question later on. I wanted to.
So don't ask anything. Don't ask anything which is not covered so far.
Okay. I was going to ask about the constituent. I mean, of the dynamics, basically, means of the white dwarf. Means white dwarf, as we have heard, that it is a dead kind of a star which will just.
No. Abhijit, yes. Abhijit, please don't ask those general questions now. That can come later.
Okay, sir.
I just want any questions on what I have covered so far.
Okay, sir.
Any other question? No, all right. So I'll proceed. Okay. So now, now I have covered my introductory part, and I will go into a little bit of the theory right now. So now here is something else which you have, which you already I'm sure have learned, is that if you take a star on the main sequence, or in fact, yeah, the main sequence or star which is hydrostatic equilibrium. Now you know that the sun, for example, has retained its size for billions of years. So if I take the sun and take a small little bit of matter in it, then what are the what are the forces acting on it? One, you have got the force of gravity, which is trying to pull it toward the center, and the other force which is acting on it is the thermal pressure. Because you see that if the matter is at high temperature, and there's a thermal pressure P is equal to NKT, which you see here in this equation, and so the small little element has gravity pulling it down and the thermal pressure pushing it up. And then these two forces are exactly equal, as a result of which you get what is known as hydrostatic equilibrium. And the equation which describes the equilibrium is a very simple equation, which I'm sure you have seen before, is that dP by dr, that is the pressure gradient, is equal to minus G into the mass. This is not the total mass of the star. This is the mass which is there within the sphere with the radius at which the element is. Mr times rho, which is the density, upon r square. R square is the distance of this mass element from the center. So this is the hydrostatic equilibrium equation. It is very simple. It cannot be solved easily because the number of variables is more than the number of equations. This is just one single linear equation. And but one can get marvelous insights from it. The first insight. Now dP by dr is the gradient of the pressure. So I can approximate that by the pressure at the surface, which is taken to be zero. So pressure at the center minus the pressure at the surface, which is taken to be zero, times this distance, which is equal to the total radius of the star. So I can represent this particular pressure gradient by the simple thing here, the central pressure upon the radius of the star. So if I do this replacement, then I can get for the density, and I know that the density rho is equal to 3m by 4 pi rp. This is the average density. If I put these two relations into this equation here, then I'll get the central pressure is equal to gm square by r to the 4. So, so now you see here is that I combine that with the ideal gas equation of state, and I get the temperature at the center, which is 2 into 10 to the 7th million Kelvin into m by m solar and r by r solar. So for the sun, this is 1, and the temperature is about 20 million Kelvin. The actual value is about 15 million Kelvin. And you see that this equation also gives you, here I can write this as P by M. So PC is equal to Gm square by r to the 4, and I can write this as PC by M is approximately equal to Gm by r to the 4. Please remember this, I'll be using it quite soon. Right, so now, now let's look at this something which you are again completely familiar with, is that this is the size of the atom. So you have got an atom here with with protons and neutrons and electrons going around them. And what is the size of the atom? So you'll see here that the atomic radius is typically 5 into 10 to the minus 9 centimeters. You will recognize this is simply the Bohr radius. Now, this is just representative. The actual radius could be some, this factor will be different there, but 10 to the minus 9 is very important. And what is the size of the nucleus? It was first discovered by Lord Rutherford that the nucleus is very, very much smaller than the size of the atom. It is 10 to the minus 13 centimeters. Right? So now let us do a simple calculation. So you have got a star mass m radius r. So the density is m upon 4 pi by 3 r cube. So what would be the number density of particles? The number density will be the matter density divided by the average mass of the particle. The average mass of the particle would be mu times mp, where mu is the molecular weight. What I'm doing here is I'm just taking it to be a gas of hydrogen for simplicity. You can just stick it mu wherever mp is and get the correct, more correct result. And so this is equal to this one. Now, well, look at a very important concept. So now let us say that there are all these gas particles in a gas has got all these particles. You can imagine, take any one particle and draw a sphere around it until you reach the next particle. Right? So what I'm doing is that I'm just thinking of dividing the gas instantaneously. I mean, because all the particles are moving, so this can only be true instantaneously. I'm surrounding each particle by a sphere. And then the size of that sphere is such that there's a particle here and the next particle will be here. So now let us suppose that the size of this is L. Right? So then what is the volume? So it is L cubed. There's a 4 pi by 3, let's forget it for the moment. So the volume of this is L cubed. And how many particles are there in this volume? By definition, there is one particle. Right? So therefore, if I take the particle number density, which is N, and multiply it by L cubed, I will get the number of particles in the sphere. And how much is that? How many particles are there? There is one. It should mean that with this construction, when L is the interparticle distance, then NL cube is equal to 1. So therefore, what is L now? The interparticle distance, L. So, so that is equal to n to the minus 1 by 3. Please remember this. If n is the density of a solid or a liquid or a gas or whatever, then the average interparticle distance is n to the minus 1 by 3 approximately. So it is given here. So now I put in the constants. If I were in front of you, I would actually put in the constants of the board to give you a feeling for it. But if I put in all the numbers, then I'll get L is equal to 10 to the minus 8 into this factor and to this factor. So for the sun, then L will be equal to 10 to the minus 8 centimeters. And what is the Bohr radius? 5 into 10 to the minus 9 centimeters. And so, even assuming that the density of the sun is uniformly distributed, the matter in the sun is uniformly distributed, the interparticle distance is greater than the Bohr radius. But let us see what happens to a white dwarf. So that the radius is about 100, the radius of the sun. The mass is more or less the same. So the interparticle distance now is 10 to the minus 10 centimeters. So which means that the interparticle distance is less than the radius, the Bohr radius, but it is much, much greater than the nuclear radius. So what is the use of all these things? Now let's just imagine, because this bothered Eddington very much, and then he discovered the solution to it. Is that you know that the density of matter in the white dwarf is very large, and therefore it was quickly realized that the interparticle distance will be smaller, much smaller than the atomic distance. But if that is true, then it could no longer be a gas, because, for example, when on the Earth, when you bring in a substance, if you bring a particle to be much smaller than comparable to the radius to the Bohr radius, then the atomic interactions will dominate, and as a result of it, there will be a repulsion, and as a result of which you will get a matter in a different phase, right? But it was realized by Eddington that this is not a real problem in a star, because the temperature inside the star is very, very large. And therefore, the matter in the center of the sun, for example, will be completely ionized. The atoms, the nuclei are totally, the electrons are all completely separated from the nuclei. When that happens, what is the size of the particles? Because electrons have zero size. And the nuclei we have seen has got size of 10 to the minus 13 centimeters. So therefore, it was realized that even though the matter in a white dwarf is so dense, but then because the matter is completely ionized, the interparticle distance is much smaller than the interparticle distance is much greater than the size of the particles. And therefore, the concept of a gas is possible. Right? So then what is the lesson that you learn from here? Is that as the density increases beyond all our normal limits of density, then in order for the substance to have the properties of a gas, you require very high temperatures. And once those high temperatures are there, then you'll have no problems. Okay. Now, one more calculation. You know that this is the kinetic energy of an electron, and that is equal to 3 by 2 kT, because an electron has got classically the 3 degrees of freedom, and then this is the usual relationship. Now, in a star, we have seen already that the temperature is equal to Gm by Kr. So, the square of the electron momentum in terms of the stellar properties can be given by this expression. Completely trivial, and you can derive it yourself. Right? So now, this is the momentum. Now, if I take L, which is the interparticle distance, and then I take the typical momentum, P, which we already derived, and cube it, and then I get this particular expression. Right? Now, if I put in the numerical values of, then I get LPE is equal to 500 times H cube. Okay, so it turns out, H has been introduced here. And then you see that you get these. Therefore, for the so when you reach white dwarf densities, then LPQ is equal to 0.5 times HQ. So do you see this? So therefore, this should remind you of the uncertainty principle, right? Because you know that delta X into delta P is approximately equal to H according to the Heisenberg principle, will be greater than or equal to H. So what does this warn you? This tells you that, look, when you reach white dwarf densities, even though it continues to be a gas, then it is going to be a gas which is governed by the principles of quantum mechanics rather than being a classical gas. So this is the thing, and which is what people like Fowler realized soon after the white dwarf measurements became available. And quantum mechanics was invented. And so they said that we need to apply quantum mechanics to the study of white dwarfs. All right. So what is this now? So this is the Maxwell-Boltzmann distribution. So when you've got a gas, an ideal gas, where what do you mean by an ideal gas? An ideal gas is where the particles are non-interacting. They interact only when they touch each other. So this is absolutely ideal gas. Okay, then you know that the distribution of momentum, how many particles are there with momentum between P and P plus dP and within a volume element dV, and that is given by the Maxwell-Boltzmann distribution, with which all of you will be familiar. 4 pi p square upon this constant temperature here, e to the minus p square upon twice m kT. And if you plot this for particular temperatures, so you'll see this curve. This is for 100K, 300K. So as you increase the temperature, the momentum keeps increasing because the particles are getting more and more energy. The momentum, typical momentum increases, and the distribution spreads out. The area under the distribution remains the same because the number of particles is the same. Right? And where does the maximum occur? The maximum occurs at square root of 2 twice ME kT. And the average kinetic energy is 3 by 2 kT. And the pressure for such an ideal gas is given by rho kT by mu mp. So you are completely familiar with this whole thing. Right. So now, it should be now. Let us say what will happen if you go actually to quantum mechanics. Right. When you go to quantum mechanics, now let us see. Let us take a volume momentum between P and P plus dP. Okay, so so what is the volume here with these shells? It is 4 pi p square, which is the area of the sphere times dP times dV. Right? Now, so this is 4 pi p square dp is the volume, is the momentum part of it, and you have to multiply that by the small little volume element. Right? And this is the volume in configuration space, this is the volume in momentum space, and therefore this is known as the phase space volume. Now, you can, what is the number of quantum shells which is there in this particular volume? You simply have to divide by h cube. Okay. Now, what does Pauli's exclusion principle tell you? It tells you that in every small element of phase space like this, there can be only one particle. But we have to take into account also the spin of the electrons. If we are trying to accomplish spins there, because the electron has got two spins, two spin states up and down, and therefore you have got, these are the number of quantum shells, but there can be two electrons because of the two states per quantum shell. So what does it tell you is that Fp dp dv, which is the total number of particles in this particular phase space volume, that must be less than 8 pi p square by h cube dp dv. Right? So what is this? This is simply Pauli's exclusion principle. All right. Now you come to the right here, and then so this is your Boltzmann distribution, and as the temperature increases, you see that the distribution flattens out, as I already showed. And this red line here, actually, this red line is simply Fp. This is proportional to p square, which is just a parabola, okay, which goes up there. And what does Pauli's exclusion principle tell you? Is that the number of particles must always be below this red line. So you see, for this particular Maxwell-Boltzmann distribution, there is no problem at all. All the number of particles always is below the red line. Here, there's a little bit of problem on this side for temperature. And with temperature of 10,000 Kelvin for this particular density, you'll see that there's a big problem. Okay, meaning that the number of particles which are required by the Maxwell-Boltzmann distribution far exceeds the number of particles which are required, which are allowed by the Pauli exclusion principle, which is again tells you that for such conditions, and which are the conditions which obtain in white dwarfs, you cannot continue to use classical laws. You have to go to quantum laws. Okay. Now we consider what is known as a degenerate electron gas, and it is called a completely degenerate electron gas. This all sounds very fancy, but the concepts are very, very simple within quantum mechanics. So a gas is said to be degenerate when quantum mechanical effects have to be true, which we have already done by saying that yes, we must be sure that we do not violate Pauli's exclusion principle. So now let us consider a gas which is at a temperature T is equal to 0. Here itself, the classical physicist would say no go. Because first of all, in classical physics, classical thermodynamics, you can never ever reach the temperature T is equal to 0. And that is because at T is equal to 0, all motion will cease completely. The energy will be 0. But that is not true in quantum mechanics. Because let us consider a gas with T is equal to 0. Let us start with a certain number of electrons. Right, so now what will happen is that when you have got these electrons and you want to pack them into the gas. So here you are doing it per unit volume. As the volume increases, there will be more and more electrons. So what is happening here is, let's just look at the diagram. Here is P and here is Fp. And then you will find that at the lowest momentum state, we can put 2 electrons. There will be 0 electrons. When we go to a slightly higher momentum, and then you see that we can have 8 pi p square by h cube electron. As we go on increasing p, there will be more and more electrons which are accommodated. Until you come to a particular p, at which is the Fermi momentum, we have accounted for all the electrons which are there in our ensemble. Right? So then what happens is that up to the Fermi momentum, all the shells are completely filled. Outside the Fermi momentum, the shells are not completely filled. Right? So, so therefore, this is a very simple distribution. Fp is equal to 8 pi p square by h cube for p less than pf. And Fp is equal to 0 for p greater than pf. So what is the total number of electrons then? It is equal to, this is per unit volume. So it is equal to, I take Fp dp and integrate it. So then I'll get 8 pi by 3 p cube by h dp. That's all. So now I define a parameter x, which is known as the relativity parameter, which is equal to the Fermi momentum Pf upon MEC. Now you shouldn't ask me what is the Fermi momentum, meaning that what is the value of the Fermi momentum. The value of the Fermi momentum actually comes out of this, in the sense that NE is now written as 8 pi MEC cube by 3h cube times x cube. So you give me an NE. Suppose you tell me that NE is equal to 1000 particles per centimeter cube or 1 billion particles per centimeter cube. Then I will invert this equation to get a value of x. And then I will get, from that x, I can get the value of the Fermi momentum. And then I know up to what shell it is completely filled. So then what is the pressure of this electron? You know that pressure is simply equal to the momentum which is conveyed to a surface area per unit time, unit surface area per unit time. And you could do that calculation, which I'm not going to do here. And then you get expression for the pressure, which is f, a given function f, and I did not write out the function, that's x, where x is equal to the Fermi parameter. Right? So now, now we consider a case where x is much less than 1. And x is much less than 1 means that the Fermi parameter is much less than MEC. Which should mean that all momenta are much less than MEC, so the particle speeds are much less than c, so this becomes a non-relativistic gas. On the other hand, when x is much greater than 1, then you get a relativistic gas, right? Because the momenta are much larger than MEC. So when x tends to 0, if one can show that fx goes as x to the 5. You know, there's an expression for this, and you just take x much smaller than 1 there, and you'll get x, fx goes as x to the 5. And which means that the pressure PE goes as rho to the 5 by 3. And what is this an equation for? This is an equation called, it's called a completely degenerate. Why is it called completely degenerate? Degenerate because quantum mechanics is important. Completely because the gas, it is at a temperature of T is equal to 0, it's a fully degenerate gas. And because X is much smaller than 1, it is a non-relativistic gas. On the other hand, if you come to X becomes much larger than 1, then then one can show that Fx goes as X to the 4. So which would mean that the pressure, because you see that here I got x cube, here I got x to the 4, so which means that the pressure goes as rho to the 4 by 3. And this is a completely degenerate relativistic gas. So you'll see that by going from non-relativistic to relativistic, we are changing the index from 5 by 3 to 4 by 3. So you will say that, my God, why are you making such a big fuss about it? The point is that it is because of this change that the Chandrasekhar limit exists. And this kind of an equation where the pressure goes as a power of the density is known as a polytropic equation of state. So the general polytropic equation of state is that P is equal to K rho raised to gamma, and where N is equal to 3 by 2 corresponds to gamma is equal to 5 by 3, and N is equal to 3, which is here, corresponds to gamma is equal to 4 by 3, which is here. Right, so now you see that this equation of state is quite fundamentally different from the equation, your usual perfect gas equation of state, which is P is equal to rho kT by mu NP, because there is no temperature. The temperature is 0, but in spite of the 0 temperature, you got a finite pressure. All right, I think that I'll stop here because I may otherwise overwhelm you with a number of facts, and I'll go to the rest of it tomorrow. So I'll be happy to take questions. Any questions, please?
So people who have a question, they can raise your hands. So today I guess there is no question. So okay.
Oh, there's one question I can see here. Somebody is asking a question.
Yeah, so let me unmute him.
Hello, sir.
Yeah.
Hello, am I audible?
Yeah, yes, please.
Yeah, sir, I just wanted to ask for n equals to 0, what would the polytropic equation represent?
So that's just pressure is equal to constant. It doesn't represent anything. Right? So it is a thing with pressure is equal to constant. The gas with pressure is equal to constant. So just look up polytropic equations and you will see what are the ranges of n and so.
Okay, okay, sir.
From, yeah. What fraction of radiation pressure? Yeah. What is the question, please? Can you, the next question, what fraction of radiation pressure is contributing to the overall equilibrium of white bars? All right. Now, this is a very good question. Well, I can even ask another question. What fraction of normal gas pressure is contributing to the overall equilibrium of white bars? So I'll come to this tomorrow. It's a very good question. Yeah, there's some other question I can see here. Unmute ourselves. I learned that white dwarfs are supported by degeneracy pressure and not thermal energy. So shouldn't they cool down instead of being so hot? Yes, these are all very good questions. The problem is that I had to first cover the basic theory before I can answer questions like that. So tomorrow I'll do it. The cooling of white dwarfs is a very important topic. All right, if there are no more questions, then we'll stop. Thank you very much. See you tomorrow.